Thank you, thank you. The molecule is going to be trans. The groups attached, they are in the opposite direction. So the molecules would be attached. So for cis-trans isomers, they are examples of the geometrical isomers. The new type of isomers that we are going to learn in this chapter, they are pair of enantiomers. We are going to learn about also diastereomers. Diastereomers, these are compounds that they contain a chiral carbon. A chiral carbon, it means we're just going to move. Chiral carbon is a carbon that it contains 4 different groups attached to it. So if you have 4 different groups attached to your to the carbon, then the carbon is going to be a chiral carbon. Chirality or handedness, that is, it means that the compound and its mirror image are not superimposable. So the right glove does not fit the left hand, or the left glove does not fit the right hand. So if they are different, so you have 2 objects with the same connectivity. It's made of exact same bonds, and the shape is the same in terms of the connectivity, but the arrangement in the space is in a way that if you try to superimpose it, they are not going to superimpose. So if you take your 2 hands, they are, if you slide it over one another, that is not going to 100% cover each other, even though they look the same. Okay, even though they look the same, but they are not. They are mirror image of each other, and chirality comes from this name of the handedness. Okay, chiral. What is not allowed is to move the molecule out of the plane, like flip it. This is not allowed, but 2 conditions. If you try to superimpose, it doesn't superimpose. And if you rotate by 180 degrees, still it does not superimpose. So moving by 180 degrees is also allowed in order to see if your 2 molecules are going to superimpose or not. If they don't superimpose directly, if you move change one by 180 degrees, then you have 2 molecules that they are pair of enantiomers, means that they are mirror image of each other, and they are not superimposing. So first, they should be mirror image of each other, and second condition is that they should not superimpose each other. And the third condition, if you move it by 180, it doesn't superimpose each other. Then your molecule, these are 2 separate molecules. They should be named separately, and they have slightly different properties. And you have to determine what is the exact name for each one of the two compounds. Now, your objects that they look, with the superimposed mirror images. You have the example of this fork, or if you have this glass that is completely symmetrical, and then you could get you could see the mirror image is superimposing. So this compounds, the pictures that you see down here are the shape of the objects that they are not chiral. They don't look like the hands, that they do not superimpose each other. So you have achiral, and this is a chiral object that you have. For molecules, they could also be chiral. When we study actually the molecules to see if they are chiral or not, and how does the chiral molecule look like? You have, going to make just one chiral molecule here. Say if you have hydrogen attached to one carbon, carbon with 4 bonds. So your molecule, conditions for your carbon to be chiral, it must be sp3. It must be sp3 carbon. That means you must have 4 bonds. And those 4 bonds, they must be different. So they must be 4 different bonds attached to the carbon for your carbon to be chiral. Okay. This carbon, this molecule is a chiral molecule. You could see it, chiral molecule. At the center, this carbon, central atom here, this carbon is a chiral center because the 4 groups attached to it, they are different. Now, if you have the mirror image of this molecule, I'm going to make the mirror image for you. I wish you had the model so you could make it for yourself as well. So if I'm trying to make the mirror image of this molecule, I have to put this way, the yellow color, and a black color. Like, if I have the 2 mirror images, do you see these 2 as mirror images? If I have the 2 mirror images, then you bring it, try to superimpose it. The black color and the red color, they cover each other. But when you look at the yellow and white, they are not covering each other. So even though 2 of the atoms or 2 of the groups, they superimpose, but the others who do not superimpose. So these 2 are mirror images. And if they are mirror images, they are non-superimposable. They are 2 different molecules. So even though the groups attached to the carbon, they are the same, but this molecule on my right hand is different from the molecule on the left hand. So we have to name it differently. And in this chapter, we are first learning what are the conditions for a compound to be chiral. A chiral compound, one of the most popular one is the compound with the chiral carbon. A chiral molecule, it contains chiral center. What is chiral center? Is the carbon that is attached to 4 different groups, and your carbon is sp3. For chiral carbon, you have a sp3 hybridization for the carbon. So a chiral carbon, a chiral compound is going to result from a compound that has chiral carbon. That compound and the mirror image are not superimposable. And if they are not superimposable, these 2 compounds are different compounds. And we are going to learn also how to name these compounds. Each one separately, we learn how to name it in chapter 3. And with different groups, we learn to name priorities, and then we are going to learn one group, functional group in each chapter. But how do we differentiate between these 2 molecules? One is going to be named as S enantiomer, the other one is going to be named as R enantiomer. So we are going to learn about how to assign R or S configuration. So the configuration is different. That means the arrangement in the space is different between the 2 molecules. Okay. The arrangement is different in the space. For hybrid for the chiral carbons, these are some of the examples that we have. For this molecule here, you have 4 different, so for octanol, you have an OH group attached to the carbon, you have a hydrogen that is attached to the carbon, you have butyl group attached, and you have a propyl group attached. So you have 4 different groups attached, so your molecule is is chiral. If you have a compound like a CH3, CH2, CH3, is there any chiral carbon in that molecule? In order for a compound to be chiral, it must have 4 different groups attached to it. What about if you have a CH3? So there was no chiral carbon for propane. What about this molecule when we have H and OH attached to it? Is the second molecule, molecule B, chiral or not? Does it have a chiral carbon? Do we have a chiral carbon for compound B? No, because you have 2 of the same groups of the methyl group attached. So as long as you have 2 same group attached, your molecule or your carbon is not going to be a chiral carbon. So sometimes this H and OH is very similar to H and OH in this molecule, but the size of the carbon chain on either side of left and right, these alkyl groups must be different for the compound or for this carbon to be chiral. So it's only chiral if all 4 groups are different from each other. For this example, the second example, 2-bromobutane, you have a hydrogen, you have a methyl group, bromo, and you have an ethyl group, 4 different groups, and that makes the molecule to be chiral, or the carbon is chiral center. We have a chiral center, and for this molecule also. For this molecule, we have chiral center because we have ethyl group, methyl group, and we have a isobutyl group attached to it. So if we have 4 different groups attached to it, these are examples of chiral carbon. And why we are emphasizing on chiral carbon, because compounds that they contain chiral carbon, they are often chiral molecules. And if they are chiral molecules, that means the compound and the mirror image is not superimposable. So basically you have 2 different compounds. With respect to each other, these 2 molecules are called pair of enantiomers. Pair of enantiomers are stereoisomers or geometrical isomers, with the condition that these 2 molecules, they are mirror image of each other, but they are superimposing. Non-superimposable mirror images are pair of enantiomers. We learn about a few other definitions also, but pair of enantiomer is the first one that we talk about. So if you have the molecule and you have the mirror image, these 2 molecules with respect to each other, these are pair of enantiomers. They are mirror image, but not superimposed. A molecule that is achiral. Why this molecule is achiral? Because you have a methyl group and another methyl group attached to the same carbon, so the 2 groups are not different. So all 4 groups are not different. So these are achiral molecules. Perspective formulas. How would you how would you draw the perspective formula for a molecule starting from condensed structure formula? So if you have a condensed structure formula, how would you go from this molecule to the perspective structure? So this is basically perspective structure. So you want to make sure to use your chiral carbon as the central atom. So use your chiral carbon as your central atom in this case. You use 2 dashed line, and the 2 dashed line must be adjacent to one another. So you can't use this dashed line and then use this one as a dashed line. So it has to be 2 adjacent dashed line. You have 1 carbon, use 2 dashed line, and they must be adjacent. Then you use 1 dashed wedges and 1 solid wedges. What does solid wedges means? It means that wedges and dashes. So wedges means that this group is coming toward you, and the 2 dash line means that these 3 elements or these 3 groups are on the same plane. So let's say if I'm holding this molecule, the red, yellow, the group of red and yellow with the carbon in the central atom, they are in the same plane. So basically, if I pass a plane through this, it was going to cut through the red, yellow, and the black color. The white one is coming toward you, and the black one is going away from your view. So if you were going to draw this structure that you see at this point, you would draw the red color using dash line, yellow color using the dash line. You would draw a solid wedges for the white and dashed line for the black color. So you have those 4. So you want to make sure that the 2 dash lines are adjacent to one another. So they are adjacent. So 2 dash line, have a dash line here, a dash line here, and then you have the wedges and you have dashed wedges. So the first one, when you draw the first one, the second one must be the mirror image. So if you have a mirror here, these 2 are mirror image with respect to each other. How would you assign R and S? You have to give priority to the groups that are attached. So if I go with the strength of the color for the model that I'm holding with the strength of the color, and give the highest priority to the darkest color. So black would take the priority number 1, then would be red color, that is priority number 2, and the yellow color, priority number 3. White color here is going to be priority number 4. So 1, 2, 3, and 4. I have to hold the molecule in a way that the group with the lowest priority is away from your view. So I hold this back away from your view. So I'm kind of showing you. So if I bring it this way, the hydrogen is coming toward you. If I'm going to just make it look like away from your view, even though it's in my view now. So away from your view. And then you start numbering with the priority, going with the highest priority number 1, 1, 2, 3. If you're going 1, 2, 3, is it going clockwise or counterclockwise? So if it's going 1, 2, 3, 1, 2, 3, and it's moving clockwise, then this molecule, the configuration is going to be R configuration. So when you have your perspective molecule, where one bond is going away from you, one coming toward you, and then 2 are on the same level or same plane, going from highest priority to lowest priority while holding the number 4 away from your view, 1, 2, 3. If this is clockwise, then it's going to be R configuration, or the R configuration. We build the pair of enantiomers. So if one is R, the other one is going to be S, because these 2 are mirror image of each other. When you have pair of enantiomers, one would be R, the other one must be S. If you find the configuration for the other one also R, that means these 2 compounds are the same, so something went wrong. So I'm going to leave this molecule down and then try to assign the priority for the enantiomer, and white color takes the lowest priority. I keep it away from your view, and you're going from darkest color to the lightest color. So we already had that assigned. Black with the highest, red second, and then yellow would be the third. So if you're going from black to red to yellow, is going counterclockwise. So if it's moving counterclockwise, the configuration for this enantiomer is going to be S, and it was expected to be S because we assigned R for the other enantiomer. So what happens if I flip this molecule and I bring the lowest priority, or the hydrogen, or the lowest priority number 4 toward you, moving toward you? Now, if you are moving from, we assigned S for this, right? S for this molecule. Now, if you are moving from black to red to yellow, now it's going to look like that is moving clockwise. And if it's moving clockwise, the configuration is going to be R, but this was a S molecule. What's the difference? The difference is that you didn't follow the first rule, that this must be the white color with the lowest priority must be away from your view. So if you flip it, if it comes toward you, then you have to switch the rule. You say, if it's clockwise, it's going to be R, and if it's counterclockwise, it's going to be S. So you have to basically check follow both rules. Or if you are changing the rule, you have to change your assignment also. So if the group with the lowest priority is away from you, clockwise is R. If the group with the lower priority is toward you, is coming toward you, then the clockwise is going to be S. And we are using that in the in Fisher projection, which you will learn soon. Now, how do you assign priority for groups attached to the chiral carbon? Rule number 1, if you have, let me just put in one example here. Let's say you have a carbon with bromine attached, with CH2 attached here, and you have CH2, CH3, and hydrogen attached. Okay. The element directly attached to the chiral center, this is the chiral center. The atom directly attached to it with the highest mass, or atomic mass, would take the highest priority. The element or the atom attached directly to the chiral carbon with the lowest atomic mass is going to be lowest priority. And highest priority we give number 1, lowest priority 4, because there are only 4 groups. So it's obvious in this case hydrogen is going to be 4, because we don't have anything smaller than hydrogen. So hydrogen is going to be 4. Between bromine, carbon, and carbon, which one would take the highest priority? Bromine would take the highest priority because it has much higher, the atomic number for bromine is 35, for carbon is 6. So bromine 80 atomic mass, and this one is going to be 12. So bromine would take the priority 1. Hydrogen would take priority 2. What about the other 2 group? We have a carbon and carbon. Since is a tight position, since both of them are the same, they are tied, we have to move a bond away. Now, in a methyl, this carbon is attached to 3 hydrogens. For the ethyl group, the carbon that is directly attached to the chiral center is attached to one other carbon. It's 2 hydrogen and 1 carbon. So we have to move 1 bond away. So if the first one is carbon and carbon, then bond away. For the ethyl group, you have a carbon. For methyl group, you have only hydrogens. So this is going to be 2, and this is going to be 3. Now, if we had the perspective structure that we could see the hydrogen is going away from you, then going 1 to 3 to 4, I'm sorry, 1 to 3, 1, 2, and 3. This is counterclockwise. If the hydrogen going away from you, the configuration is going to be S, because it's counterclockwise. When you are going from highest priority to lowest priority, you could bypass 4, because 4 is is away from your view and is not blocking this. But you cannot pass 3, priority 3, because you cannot say, if you're going from 1 to 2, you cannot go this way 1 to 2. That's not possible. You have to go from the side that there is no blockage. So you have to always follow the trend, like 1, 2, 3. It's okay to pass 4, but it's not okay to pass priority 3, because you have a group here that is either the same level or is coming toward you, and you cannot pass them. So you're going 1, 2, 3 if it's counterclockwise. Since hydrogen is going away from your view, because it's showing with the dashed lines or dashed wedges, then it's going to be S. So let's look at the rules, or maybe one more example here. If you have one more example here, probably is better. If you have carbon, you have hydrogen. In this case, you have a CH3 in this side, and then you have carbon. Which one takes the priority? Which one has the highest priority in this case? If you have double bond, you count as 2 bonds. Okay? So in this case, lowest priority is clear. Hydrogen takes the lowest priority. And then the second, or number 3, is going to be the methyl group. Between the ethyl group and ethene group, you have this carbon, you go one bond away. So with the first connection, they are the same. So this is the first move. The first connection is the same. So you're going to move with the second connection. The second connection, this carbon is attached to 1 carbon. For the second connection, this carbon is attached to 2 carbon. So that makes this group higher priority compared to the ethyl group. So this is going to be priority number 1. This is going to be 2. That's 3 and 4. So let's look at the rules. The greater the atomic number directly attached is going to take the highest. And if you have a tie, all positions are the same, then you move one bond further until you find the point of difference. If you have a double bond, that means it's attached to 2 of the same. If you have a triple bond, that means it's attached to 3 of the same element. So you count as 3 bonds. When you have isotope, the heavy isotope is going to take higher priority compared to the lighter isotope. How do you assign the priority? We talked about the priority, but if when your priorities are assumed, then going from 1 to 2 to 3, if it's clockwise, is going to be R. If it's counterclockwise, it's going to be S. That's with the condition that with the lowest priority must go away from you. So you have to hold the lowest priority away from you. So when you say clockwise, you see here you're passing 4, but you cannot pass the other one if you're passing 4. So when you say clockwise or counterclockwise, that means like clockwise, like a R. Clockwise would be R, like turning the wheel to the right side, to the clockwise. And then counterclockwise, it's making it like left turn or S. So counterclockwise would be this one, and then clockwise would be this, like right turn or left turn, opposite. For R and S, I need you to help me with configuration of the molecule on the left side. What takes the highest priority? Unless it's repeated, but BR would take the highest priority. So we have 1, and priority 2 would be ethyl or methyl. Ethyl group 2, and then priority 3 would be methyl group, and 4 would be hydrogen. Now the hydrogen is going away from you, so this prospective molecule is proper for us to determine the RNS with no complication, no changing, changing the rules or making the rules opposite, because the lowest priority or hydrogen is going away from you. Now going from 1 to 2 to 3, the molecule on the left side, 1 to 2 to 3 is going to be S configuration, and the priorities are the same. So for the second molecule or the molecule on the right, I am going to write the priorities that you gave me, going from 1 to 2 to 3. Now this is a clockwise, and the molecule on the right side is going to be R configuration. So we have the S configuration and the one. Ethyl takes the priority over the methyl because the I'm looking for a page here. Why ethyl takes the priority? We have to move from carbon. So this is the ethyl group. This is the methyl group. You have a hydrogen and you have a Br. Chiral carbon here. The first atom attached for the Br is obvious. We had enough practice for it. So it's going to be priority number 1. It's 1. Hydrogen is going to be 4. So we have 1 and 4 already determined. Between 2 and 3, you are going to move 1 bond. You move 1 bond here is a tie position. So you cannot decide based on the first bond that you are moving. So you have to move away from the chiral carbon, further away from the chiral carbon. So if you move further away, here is going to be understood hydrogens, because we know that carbon has 4 bonds. So if 1 bond is carbon, the other 3 are hydrogens. So if you move one bond away, you are going to reach to hydrogen. You move one bond away from this one, you are going to reach to carbon. So we found this is the first move. First, this is the second. With the second move, we found point of difference. The first move, both of them end up with carbon. The second move, because you have to be even and fair to both sides. For the right side, you move second bond, the second bond away from the chiral, and that ends up with the carbon here. With the second move to the left side is going to give you hydrogen. Which one takes the priority? The one that is heavier. So point of difference was here compared to the hydrogen, carbon compared to the hydrogen. That's why ethyl in general, it takes higher priority compared to methyl. Did I answer your question? Perfect. Okay. When you have the priorities assigned, you're going from 1 to 2 to 3, and you can, again, counterclockwise or clockwise, then you have R versus S. For counterclockwise would be S. For clockwise movement, when we are moving from priority 1 to 2, 3, is going to be R configuration. So you notice that here we are showing hydrogen in the dashed line. With the dashed line, that means it's going away from you, because that is the rule. If hydrogen comes toward you, then the configuration is going to be opposite. So the group with the lowest, if you don't have hydrogen attached to your chiral carbon, the group with the lowest priority must go away from your view. And to show the group going away from you, you are using this dashed wedges, and the solid wedges, it's coming toward you. In perspective molecule, you have 2 dashed line that it shows bonds that are coming in the same plane. So this part of the molecule is in the same plane. This is going away from you, and this is coming toward you. And same thing for the others. Okay, what happens if you have hydrogen already given in a molecule that hydrogen is coming toward you? Remember, if we have hydrogen away from us, and this is giving us like counterclockwise S, if I bring it toward you, it's going to move like clockwise. So what we can do, we can determine the priority. We can, if the priority for hydrogen is 4 and it's coming toward you, because this is the given structure, we say, okay, going 1 to 2 to 3 is clockwise, and because it's clockwise, this is going to be R, but since hydrogen is coming toward you, you have to say this is S. Okay, or the other way that you could do, you can either remember that hydrogen must be away from you, and if it comes toward you, it is going to change the configuration. So if it's R, you must report as S. If it's S, you report as R. Or switch it. Take the hydrogen back like this. Since you take the hydrogen back, then the methyl is going to come toward you. So you cannot have 2 dashed lines. You cannot have both methyl group and hydrogen away from your view. So if hydrogen goes away and methyl comes toward you, now you determine the you move from priority 1 to 2 to 3 is clockwise. Is clockwise for a change molecule. Is clockwise for 90-degree rotation or 90-degree switch, or one switch. One switch meaning that you take one of these groups that was coming toward you, you take it back. With the one switch, you have to change the configuration. So if you determine R after the switch, original compound must be S. Or you could just determine the configuration here and say it's clockwise, but since hydrogen is coming toward me, it has to be assigned opposite, so it would be S configuration. Questions? So we find the chiral center. After we find the chiral center, we assign the priority attached to the groups that are attached to the chiral center. Hydrogen always, if one of the bonds attached to the carbon is just hydrogen, that would be always lowest priority, or number 4, because that's the smallest group that you could find. You look for the first atom directly attached to it, oxygen compared to the carbons. So oxygen takes the priority, is not the OH group, is the oxygen that we are counting. In this case, we are counting the carbon first, and then you move one bond away because the carbons are the same, so you have to move one bond away. If you move one bond away for this molecule on the right side, the group of on the right side here, it moves up to carbon. This one also moves up carbon. So there's no point of difference yet. So you move one more bond. So basically your third move is going to end up with bromine here and a hydrogen on that side. So bromine takes the priority. As a result, this group 2 is going to have higher priority compared to group 3. Why it's important for you to move one step at a time, one bond at a time? Because if you don't move one bond at a time, by error, by mistake, you're going to say this is going to take higher priority compared to OH. Because if you count the total mass, bromine is 80 and this is 17. So you might say this group it takes the higher priority, and that is not correct. And you have to move one bond at the time directly attached to the chiral center. If oxygen and carbon, oxygen takes the priority over carbon. You have carbon here and carbon, so you have 2 carbon. You cannot decide yet. You have to move away, look for carbon and carbon. You cannot decide yet. Then you have to move one more bond. Here you have bromine, but in this carbon, everything attached is hydrogen. So that makes the point of difference. Your third move makes the point of difference. And your point of difference indicates that this group, bromoethyl, is going to be higher priority compared to the ethyl group. Okay, this slide basically was showing that you can go from 1 to 2 if you have hydrogen, like the low priority. You can bypass this or pass this, but you cannot move with something that doesn't have the lowest priority. So if you have priority 3 here, you cannot move this direction. This is not allowed, it's restricted. So you have to move properly from 1 to 2 to 3. This is the correct one. This is Are these molecules pair of enantiomers or not? How would we determine if they are pair of enantiomers or not? The easiest way is to find configuration for this, find configuration for the other molecule. If one is S and the other one is R, then we know we have pair of enantiomers. Both of them are S, it's not enantiomer, that means they are same molecule. Not every 2S it's same molecule, but in this case, if you look at this chiral carbon that assume chiral, you have OH attached hydrogen, so the groups attached are the same. Basically, molecular formula is the same, connectivity is the same, and if both of them get the S configuration, then you have same compounds. If one gets S, one gets R, then you have pair of enantiomers. If both of them are R, then you have same compounds. Okay, I need you to help me to assign priority for the groups attached and configuration. For this molecule on the left side, what takes the highest priority? Okay, perfect. OH takes the highest priority, 1. And second, it would be methyl or propyl. Propyl would take the second priority, 2. And ethyl would be third priority. And hydrogen is going to be priority 4. Now, moving from 1 to 2 to 3, we have to move this direction. Clockwise or counterclockwise? R or S? Is going to be S. And we assign properly counterclockwise S because hydrogen is going away from you. That's kind of a warning for the other one. So because hydrogen is going away from you, counterclockwise is going to be S. So since you gave me the priority, I'm going to put it already. 1, 3, 2, and 4. If you are moving from 1 to 2 to 3, is moving counterclockwise. Is the configuration R or S for the compound on the right? The move is a counterclockwise. Is this R or S? If the hydrogen was going, okay, if the hydrogen was going away from you, counterclockwise would have been S. Since hydrogen is coming toward you, then you have to assign oppositely. Okay, hydrogen is coming toward you, so counterclockwise is going to be R. Because hydrogen is going, hydrogen is on the wedges. If hydrogen is on the dashed line, it means going away from you. Counterclockwise is S, clockwise is R. But if hydrogen is coming toward you, you have to assign it opposite. Okay. Are these two pair of enantiomers or same compound or different compounds? Are they pair of enantiomers? Yes or no? Yes, because they are enantiomers because one is assigned R and the other one is assigned S. You have R and S configuration. Connectivity are the same and the configuration is R and S. So you have pair of enantiomers. That's how you determine pair of enantiomers. Or if you know the configuration for one enantiomer, S, you know that the mirror image is going to be R. Okay. Now that you know how to assign R and S, at least you know how to study, how to assign R and S. So you are set to go and do the all end of the chapter problems, read the full chapter, because PowerPoint doesn't cover every single example. So you want to practice with this. Again, you are learning a new language within the new language. Organic chemistry is a new language, and then naming of alkane was new language, and then this specific R and S configuration is a new language within the new language, so new terms, new knowledge. So you need a lot of practice with this as well. So if you were given the name for the compound, or this compound, if they tell you that this compound is the S configuration, how would you draw the S configuration or perspective molecule for this S configuration of this? So you find out this is your chiral compound. So you have your chiral compound, the chiral carbon there. You assign the priority. Nitrogen would take higher priority, that's 1. Hydrogen is 4, priority 4. This group, a carboxyl group, is going to be priority 2 in this case. And the methyl group is going to be priority 3. Why COO is a priority 2, even though it has 2 oxygen? Because the first element attached to the chiral carbon is C, is carbon. You're comparing carbon, nitrogen, carbon, then nitrogen takes the higher priority. In this case, you're comparing carbon and carbon, same, so you move one more bond. So this is O, and that side is hydrogen, so that's why COO takes the 2. So you draw the chiral center first, then you draw 2 dash lines that they are adjacent. You draw 1 bond going away from you, and you draw 1 bond coming toward you with the solid wedges, and the other one is dashed wedges. Your lowest priority hydrogen should go away from you, so you draw hydrogen next to this. Hydrogen should go away from you. Then you bring in your highest priority. You can put your highest priority in one of these dash lines. Okay? So that's your NH3. NH3 plus. You wanted to have it S, right? Because here it says S. That's how we decide where would the priority 2 and 3 should go. Because it says S, and this is your priority 1, that's your priority 1. Starting with the priority 1, draw a counterclockwise, because hydrogen is going away from you. So this S, it has to be counterclockwise. So starting with 1, draw a counterclockwise loop. So you draw the chiral center, you draw 2 dash lines to show solid bonds, and then 1 dash is going away from you, 1 wedge is coming toward you. Put the lowest priority going away from you, put the highest priority in one of the solid lines, and then draw the loop. Because it's S, your loop has to be counterclockwise. Now, the rule is if it's 1 counterclockwise, if you are moving from 1 to 2 to 3. So priority 2 has to go this position here, priority 2. So you're going to have COO bond here. And priority 3 should go up here. Okay. Did you get it? I repeated 2 times, but I want to make sure that you get it, you get the steps. So you first have your condensed molecule. From the condensed molecule, you find your chiral carbon. So this is your chiral carbon. So when you have your chiral carbon, then you look at the groups attached. You have a hydrogen, priority 4. NH3 is priority 1. CH3 is priority 2. And the COO priority 2 and CH3 priority 3. You draw 2 solid lines, 1 dashes, 1 wedges. Then you place the lowest priority, or number 4, in dashes line. You put your highest priority in one of the solid lines. And then to decide if 3 goes here or 2 goes to which point, that to determine 2 and 3, from priority 1, you start drawing a loop that is counterclockwise. Then it's going to show you easy where the 2 should go and then where the 3 should go. Okay. Questions? So if this molecule is given to you to determine the configuration of, this is the full molecule. To determine the configuration, you have priority 4 for this hydrogen, and priority 4, this would be priority 1, 2, and 3. Going 1, 2, 3 is S. So if the molecular formula is given to draw this, you start with the chiral carbon, you give the hydrogen or the lowest priority group going away from you, and then start with the highest priority, like NH3 in this case, and draw the loop, and then place the other 2 groups in. So if the molecular formula is given, you should be able to draw the structure or perspective for S or R. If the perspective molecule is given to you, you should be able to configure it. Is it S or R? So determine the configuration, or find out the configuration. Is it R or S based on the priority of the groups? Fisher projection is using, for Fisher projection you have here, if I draw the Fisher projection for this molecule, is using cross lines, perpendicular lines. If you have only one chiral center, one cross point is enough. So you only use 2 lines of the perpendicular to each other. So the cross point represents your carbon. And this is the model. We are going to put the carbon chain aligned with the vertical line. Carbon chain, vertical line, so COO and then CH3. Then the other 2 groups, they go to the horizontal lines. If you place hydrogen on this side, NH3 on this side, what would be the mirror image to this molecule? The mirror image to that molecule is going to look like this. You have NH3 on this side, hydrogen on the left side, COO would stay the same, and CH3 is at the bottom. So these 2 molecules, with respect to each other, these are a pair of enantiomers. They are Fisher projection of this perspective structure. So to move the perspective structure to Fisher projection, count how many chiral centers you have, use cross lines. If you have 2 chiral centers, you're going to use 3 lines. So you have 1 chiral center in that cross point and 2nd chiral center in this cross point. But if you have 1 chiral center, just 1 point is good enough. Carbon chain goes on the vertical line, and other groups would go on horizontal line. In Fisher projection, vertical line, this vertical line is going away from you. Horizontal line is coming toward you. So it's like this. If I hold this molecule, you're drawing the black and this yellow color in the in vertical line, and then the red and the white in horizontal line. These two groups are going away from you. These groups are coming toward you. So what happens here? Hydrogen is going away from you. So if we determine the configuration for this molecule, what does clockwise would mean here? Let's assign the priority. Hopefully with the priority is going to make a difference or makes it easier for you. So hydrogen has priority for hydrogen has priority 1, 2, and 3. Going 1 to 2 to 3. Clockwise or counterclockwise? It's clockwise. Clockwise, but what is the position of hydrogen? Hydrogen is coming toward you or is going away from you? Oh. I made a mistake. I said it wrong. So horizontal lines are coming toward you. I am sorry. Is it on the record? And I'm glad that, you know, with the practice, I realize that I'm talking about the vertical line. It goes away from you. So this way, vertical line going away from you, horizontal is coming toward you. And I'm sorry that your answer was correct based on my explanation. But hydrogen, in this case, is coming toward you. In Fisher projection, the horizontal line, it's coming toward you. Thank you. And it was yourself answering both questions in both scenarios. Okay. At least we know, you know, you're not the only one answering questions, but they have limited number answering questions. I wish I had everybody trying to participate and take turn and answer questions. So anyway, for Fisher projection, when you are using crossed lines or perpendicular lines to present the molecule, what goes on vertical line is the carbon chain, and the other groups would go on horizontal line. The vertical lines are going away from you, and the horizontal line is coming toward you. Because the hydrogen in this structure is coming toward you, a clockwise, okay, this is a clockwise, and hydrogen coming toward you, then the structure is going to be S. And we started with the S structure. What would be the configuration for the molecule on the left side? If these two are a pair of enantiomers, and I determine the configuration for the one on the right side as S, the one on the left side must be R configuration. Okay. Now, we're going to practice to determine the configuration, because this is going to be practice for Fisher projection again. We have priority 4, we have priority 1, 2, and 3. Going from 1 to 2 to 3 is counterclockwise, because to be connected again. Okay, it was just a gap. It was me, it was the system, I guess the Blackboard. Collaborate, had to calibrate or something. So, drying Fisher projection. Any question about drying Fisher projection? Vertical line carbon chain. So you have your carbon chain in the vertical line, and horizontal line would be the other elements. For R and S configuration, because hydrogen is coming toward you, going from 1 to 2 to 3 is counterclockwise in this case, so the configuration is R. 1, 2 to 3 is clockwise, but because hydrogen is coming toward you, is going to be S. Questions? It's the same molecule. Okay. Okay, if you have a molecule like this, we already know we have only one chiral center, so it's going to be one cross point. A vertical line is going to be carbon chain. Horizontal line is going to be the other groups. So we have H and OH. So which group should be written on top? Which group should be written in the bottom? It shouldn't make any difference when you have the same, like alkyl groups, both they have same oxidation number. But in this case, you have an element that has higher oxidation number. Your carbon here is going to be more oxidized. And because it's more oxidized, you are going to just place that group, the higher oxidation group, on the top, and the group with the lower oxidation at the bottom. So if you compare the OH, when you have an alcohol, compared to CO double bond. CO double bond is more oxidized compared to CO single bond. So this one would go on top and the OH would go down. We don't have example, but I just want to make sure that if you see this, you give priority to the more oxidized would go top, less oxidized would go down. We talked about those already. Okay, any questions? So what is important for you to be able to recognize chiral carbon? If the carbon is sp3 and attached to 4 different groups, that carbon is chiral carbon. If your compound has only one chiral carbon, your compound is going to be a chiral compound. A chiral compound, or they behave like they have like handedness property, means that the compound with the mirror image is non-superimposable. So if you have a compound that it's non-superimposable with the mirror image, your compound, those two are two separate compounds, and they are mirror image of one another. They are known as pair of enantiomers. Now, pair of enantiomers, first of all, you should be able to draw the structure for the mirror image. If you are given one, you should be able to draw the other one. If you are given the name of the compound, you should be able to draw the perspective structure, which we had one example, and we repeated like 3-4 times the same example. So you start with your chiral center, and then you draw 2 solid line and 1 wedges and 1 dashed. So give the lowest priority to dashed and draw one of the highest priority in one of the solid lines. If the compound is S configuration, you draw a counterclockwise loop and then place the group 2 and 3. If it's R, you draw a clockwise loop and then place 2 and 3 properly in order to follow the clockwise or the counterclockwise. If the perspective structure is given or the Fisher projector is given, you should be able to assign, is it R or is S? And all you have to do, like if you assign R or S, just follow the naming for alkane. You just give location of the chiral carbon, and then you give the R or S configuration. So if your carbon 2 is S, you would, before anything, you just write 2S and then the name for the rest of the molecule. 2S, let's say 2S 2-bromo butane. 2S 2-bromobutane. So we also give a more specific structure. So up to now, you could just say 2-bromobutane. That means bromine and the second carbon of butane. But when you say 2S, that means the configuration is in a way that is going to, if you have the hydrogen going away from you, you have a counterclockwise rotation going from priority from bromine to ethyl to methyl group. So it would be 2-bromo, 2S 2-bromo butane. Mirror image of that would be 2R 2-bromo butane. What is the difference between enantiomers and what's the similarity? 2-bromobutane, if the condensed structure is given to you, it's okay. If the perspective structure with the wedges and dashes is given to you, you must include that R or S, yes. Good question. The difference between pair of enantiomers or mirror images. The physical difference in physical property, they look very alike. They are very similar. Pair of enantiomers, they are very similar, just like similarity between your right hand and left hand. They are very similar. That means they have all same physical properties. Means that they have same boiling point, same melting point, same refractive index, same of everything. Density is going to be the same. But since there are 2 different compounds, there must be a point of difference between the 2 pair of enantiomers. The point of difference for pair of enantiomers is that physical point or physical difference in physical property. They rotate plane polarized light in different direction. Now, in order to rotate the plane polarized light, your compound must be chiral. It must be pure chiral. Even if it's like 50-50 mixture, is not going to rotate the light, but it must be chiral. It must be optically active. What does it mean, optically active? Optic, it comes from the light. Active means that this compound can change the direction of the light. Sometimes it changes to right side, clockwise. Sometimes it changes counterclockwise or to the left side. Now, if one enantiomer is going to rotate the light to the right side or clockwise, the other one is going to opposite. So it would rotate the light to the counterclockwise or left side, and it's going to be negative. The plus and minus charge or rotation of the light cannot be associated with the structure. It depends on the, or cannot be determined to the structure by looking at the structure. You actually have to use a machine, and using that machine you can determine if the molecule is going to, or that compound is going to rotate the light to the right side or to the left side. The polarimeter is designed in a way that it would generate plain polarized light. So I'm going to just use my hands, because you could see from the filters that's on this diagram on slide number 23 of this presentation, but I'm using my hands. Like, let's say you have my hands, two filters. So you have the light source here coming in, and then if I have two parallel filters, so I kind of do this, two parallel filter, the light comes from one filter and it will pass through the other filter. Okay, the light would come through one filter, and when you say polarized light, is the light that moves only in one direction. So I have my filtered light that is moving only in one direction. Now, if I have sample holder in here between two filters, between my hands, and it happens that the compound that I have here is not plain compound, or this compound is optically active, what's going to happen is going to rotate the light. Now the light comes through this plane, and then the compound that is in here is going to rotate the light, and instead of going straight through this other filter, is going to be blocked by the other filter, because now it's rotated. It wasn't going straight, and since it's not going straight, it's been rotated, it would be blocked by the other filter, so I won't see the light on the other side of the filter. How could I see the light on the other side of the filter? Now, I have to take this filter, like my left hand. I'm assuming this left hand being like a movable filter. So if I rotate this filter, if I rotate it enough for it to be parallel to the direction of the light, now light is going to pass through. So if when it's a straight or original position, the light doesn't pass through. But if I move the filter, because the light has been rotated until it's parallel, now the light is going to pass through. And I could see the light on the other side. Now, how much I had to rotate the filter, by how many degrees I had to rotate my hand in order to see the light again, that is known by the observed rotation of this compound. So chiral compound is going to rotate the light, and when it rotates the light, is going to rotate it by different degree. Now, that what degree is going to rotate, it depends on the concentration of the compound that you have. It depends on the optical activity of the compound. It depends on the light path, the pathway. Like the design of the polarimeter, they come with a 1 decimeter or 2 decimeter long cells that you can place your compound in. So the longer the light path is, the rotation is going to be more. So it's affected by the rotation, is affected by those. So polarimeter, two filters, one would be fixed, one movable. The light comes in. If your compound that you have here is chiral, is going to rotate the light and is not going to pass through the second filter, you have to rotate the filter until you see the light. By how many degrees you are rotating this other filter, this movable filter, you count how many degrees the light has been rotated. And that's, since you're going to observe that it counts as the observed rotation. So you have your observed rotation. You can calculate a specific rotation for that also. If the light rotates to the right side or positive or dextro-rotatory, to the left side is going to be negative. They just say like negative, and is going to be, that means that is moving to the left side. Now, would always S enantiomer be positive or always negative? We talked about that before. It has to be determined experimentally, and this is important. And sometimes you get this as a multiple choice question, that this rotation must be determined experimentally. You can't look at the structure and say because it's S, it must be negative, because we do have example of S lactic acid that rotates the light in right direction or clockwise, and it's going to be positive. And then you have sodium lactate with S enantiomer that you get the negative. So negative and positive is determined experimentally. S and R is determined based on the structure of the compound. So you see that when the light is rotated, then you can just measure by how many degrees have been rotated. That depends on the design of the machine. The design of the machine, it can go from total darkness to total light, or sometimes the design of the machine is in a way that half of the light will pass straight without going through the sample. So the light is divided in half. One would go through the sample and the other one would go straight without passing through sample. This way you have a point of reference to check. Like if the light is blocked and then you rotate it, how much you have to rotate to see the light on the other side. You will see that, how many degrees you have to rotate. You will have experiment for stereochemistry. You will see the polarimeter regardless of where you take your lab. Actually, it's going to be on video, but still you will see that it's going from two same shade or two different shade of the half circle. That depends on the design of the experiment. More explanation also is in the lab manual based on use of the polarimeter, how to use it, and you will get a full explanation also when we are doing that experiment as well. So what is a specific rotation? A specific rotation is rotation for 1 gram, rotation of 1 gram of the sample in 1 milliliter. So 1 gram per milliliter of the sample with 10 centimeter sample tube. So if your sample tube is a 1 decimeter or 10 centimeter, then it's going to give you the definition for a specific rotation. So we could see that a specific rotation is going to be affected by mass of the sample that you are dissolving, or the volume of the solvent that you are using, and it depends on the size of the sample tube that you are using. If you have a specific rotation for R with the positive number, if it is pure compound, the specific rotation for S would be the exact same numerical value with opposite sign. If you get a mixture of two compounds, the mixture of R and S, if the S rotates the light to the clockwise, then the R is going to rotate counterclockwise. So if you get 50-50 mixture, you will have no rotation. The net rotation is going to be 0 because you have 50-50% of the enantiomer. If one enantiomer is going to rotate to the right side, the other one is going to rotate to the left side. But since you had same percentage of the two enantiomer in the mixture, the net result is going to be 0. What happens if you have 75% of one enantiomer and 25% of the other enantiomer? What would be the net result? the net result, if one enantiomer rotates by, no, this is a 75-25. If one rotates by 75 degrees, the other one, it will rotate in opposite direction by 25. What would be the net? Very good, very good. So you end up with 50 rotation. So if one goes 75, the other one brings it back by 25, the net is not going to be 0. It would only be 0 if you have 50%, 50-50 mixture. So if one goes like to the right side by 14 degree, the other one would bring it 14 degree, is in the same tube, same concentration, is a 50-50, the net result is going to be 0. If you have a 50-50 mixture, that mixture is called a racemic mixture. Racemic mixture means that, or racemate or race mixture, optically inactive. Even though you have chiral carbon, you have chiral compound, but since it's a 50-50 mixture, it's going to have 0 optical activity. So there are limited number of compounds that they have optical activity. Those compounds, they are chiral, and they are not 50-50 mixture. You could have compound that you have more than one chiral compound. You have 2 chiral compounds, but it has plane of symmetry. Let's say you have a compound that like this. You have OH, OH, H, CH3, CH3. If you draw a line here, it cuts the molecule in exact 2/2 or mirror image. So this is like internal mirror image. Internal mirror image, even though you have 2 chiral compounds, these compounds are chiral, but this molecule is not chiral, is achiral. Achiral means that it doesn't rotate the light, and that's because of the internal symmetry or line of symmetry or plane of symmetry you have here that cuts the molecule in 2 exact half. These are cases that the compound is not chiral, it doesn't have optical activity. If you have a meso compound, if you have a racemic mixture, which is a 50-50% mixture, if your compound is not chiral, then it would not have optical activity. Okay, do you have any questions for me? Okay. Your exam 1, it's not on honor lock, it's on the responders. And exam 2, 3, and your final exam will be on honor lock. So make sure you have your webcam and reliable internet when you start your exam anytime. I mean, just like quizzes, because it's just one time, one attempt. If it was me, only up to me, that would be the case.